And we're going to finish up the last little part here of bonding, so you can hopefully complete the entire experiment later here. So again, if you can't see, you can kind of move to wherever you can see. Not the best room to finish, but we will. So again, this table is the geometries that we talked about at the end of lecture. And as I mentioned before, you are responsible for the electron pair geometry. You should pretty much have this table in your book. The molecular geometry or the shape. And again, you should know the bond angles as well for those guys. And these are pretty much the geometries that you're responsible for: linear, trigonal, planar, tetrahedral, trigonal pyramid, bent or V-shaped. And the other one that we sort of added to the list is, again, 3 electron pairs. Actually 3 electron pairs, 2 bonds. That gives us our trigonal planar. And that is our angular, which is less than 120 degrees. So that one you'll add to this list, but we pretty much have them all. And those are the 3 columns that you really need to know. As I mentioned, it is the best way to do it is just really memorization is sort of the best way to sort of do it. And I would count like it does here, the number of electron pairs and the bonds is really the best way. And it's always the central atom. Remember that if you have just a diatomic molecule, like we talked about, the geometry is always going to be linear. So that doesn't really matter. That's pretty simple. But anything with 3 or more, those are the 2 things you want to look at: electron pairs and number of bonds around the central atom. So the last thing we're going to talk about is molecular polarity. And molecular polarity is a little bit different. I'll write it up towards the top here so we can kind of see. Molecular polarity is talking about the entire molecule as a whole, whether or not there is equal distribution of electrons in the entire molecule. We talked about sometimes earlier bond polarity, and that is typically where we use that difference in electronegativity values to help us determine. And that is, again, what we use to determine between 2 elements or atoms. Will they share those electrons equally or unequally? Molecular polarity is different in a lot of cases, and there's really only one place where both molecular polarity and bond polarity basically are going to be the same, and that's with diatomic molecules. And when you have diatomic molecules, which means you only have 2 things like H2, that's the only place where both of those things are really the same thing. When you have 3 or more atoms involved, you actually have to look at a couple of different things, and we're going to talk about what you need to look at to help you determine if it's polar or non-polar. But if it's diatomic, these 2 things will be the same. And if it is 3 or more atoms, it may be actually different, the results. A dipole moment is represented by the same arrow that we've used before, this kind of dipole arrow, and it points to the side that's more negative in the atom or the molecule. And again, the back end points to the side that's more positive. So we use that arrow to indicate individual polar bonds. And we also use that basically same arrow to indicate in the entire molecule which side is more positive and which side is more negative. Only polar molecules have dipole moments. So only polar molecules have dipole moments. Non-polar molecules do not have dipole moments. So you could think of a polar molecule kind of like what we think about with a polar bond, a non-polar bond. When we have a non-polar molecule and a non-polar bond, because we have equal sharing of electrons and equal distribution of electrons over the entire molecule, it's sort of like a neutral molecule. There is no side that's more positive. There's no side that's more negative. It's sort of neutral. And when we have a polar molecule, just like when we have a polar bond, there is a side that's more negative and there's a side that's more positive because of the unequal sharing or distribution of the electrons as a whole. So polar and nonpolar for bonds and polar and nonpolar for molecules are basically kind of the same meaning. And they basically both mean nonpolar, nice even distribution, no charges. polar, we have an unequal distribution of those electrons, and we do end up with charges. So as I mentioned before, the one place where bond polarity, the difference in electronegativity, and molecular polarity are same as with diatomic molecules. So for example, if we had a diatomic molecule like H2, because these are both the same element, we would do the difference in electronegativity and we would get a difference of 0, which means that that bond there is going to be a nonpolar bond. And because this molecule only contains one bond, and because that one bond is nonpolar, that would mean that this guy also has to be a nonpolar molecule. And again, that's because it's the only bond that's present. If we had something like what we looked at today, Cl2, which we know is nonpolar as well, that bond between the two Cl's will give us a difference in electronegativity of 0. And that's going to mean that that is a nonpolar bond. And once again, because that is the only bond in the entire molecule and it's nonpolar, that would mean that this guy is nonpolar, like we saw today in the lab, that this is a nonpolar molecule. So those are pretty simple to sort of figure out if it's diatomic, just like if we had HF, and I'll write it a little bit higher, which is a heteronuclear diatomic molecule. We know that fluorine is the most electronegative. So when we do the difference in electronegativity values, if you remember, we got something like 1.9 that tells us that it is a polar bond. And we could represent that with that arrow, just like we did there. Again, drawing arrow pointing towards the fluorine, which is more electronegative, hydrogen being more positive. And because this bond, once again, is the only bond that we see there, that would mean that this guy would also has to be a polar molecule. That also means that this right here, that arrow that I drew, would be the dipole moment, where the fluorine in this case is more negative and the hydrogen is more positive in this case. So the simplest ones to figure out, molecular polarity is when you have diatomic molecules. If the bond is nonpolar, then the molecule will be nonpolar. If the bond is a polar bond, then the molecule will be polar. It doesn't matter if the bond is single bonded, double bonded, or triple bonded in the diatomic molecule. It makes no difference. It is really just what type of bond you got going on in there. And again, because it's the only bond, both the bond polarity, where we use the difference in electronegativity values, and the molecular polarity will be the same for those type of molecules. Just like CO, right? We know that CO, right, is a polar bond. And because there's only one bond in there, that would also be a polar molecule, carbon monoxide. Any questions on that? Now, if everything was that easy, that would be great, but it's not. So it does get a little bit more complicated when you have a molecule that has 3 or more atoms involved. So when you have a molecule that is 3 or more atoms, you have to look at 2 things. You have to look at, first off, is there polar bonds? So obviously, very simply, if the answer is no, there are no polar bonds, then the molecule is going to be nonpolar. But if the answer is yes, there is polar bonds, you then need to look at the molecular polarity, molecular geometry, or the shape. So those are 2 things you have to look at when you have 3 or more atoms involved in a molecule when you're trying to determine molecular polarity. So let's take an example of our friend carbon dioxide, which looks like this. We know, as we just talked about, that the bond between carbon and oxygen is polar. Once again, carbon and oxygen is in the same row on the periodic table. Oxygen is further to the right. So we do have polar bonds, and we could draw these bond dipole arrows heading towards the oxygen in each of these cases. So this guy does have polar bonds. So once again here, you may think, well, it's got polar bonds, so it would make sense that it is a polar molecule. But we do have to look at the molecular geometry here. So when we look at the molecular geometry here, we're going to look at the center atom. It has 2 electron pairs. Remember that the double bonds on both sides count as only 1 electron pair. And it also has 2 bonds, which the double bonds on both sides count as only 1 bond each. Something with 2 electron pairs and 2 bonds has a molecular geometry of linear, as we talked about today. So basically that is a straight line, right? That's the 180-degree sort of difference between those two things. So what's happening here, my pen is like the molecules, basically the straight line. I have on one side the oxygen pulling this way, and I have on the other side the oxygen pulling back the other way. And I'm actually pulling in opposite directions really hard. Is my pen going anywhere? My pen is not going anywhere because they actually cancel each other out. So although in the case of carbon dioxide that has polar bonds, because of its geometry, they actually will cancel each other out. And this will actually be a non-polar molecule. So this is a really good example that you can have a molecule that has polar bonds, but because of its geometry, can be non-polar. And that is because these bond dipoles that we draw here, these are vectors, right? And I believe in physics, you know, vectors have direction, they have magnitude, and then I fell asleep. But then I woke back up and remember the guy said, well, in certain cases, they can add to each other, and in other cases, they could cancel each other out. And situations where they cancel each other out is where they're basically pulling equal and opposites of each other, like pulling on a rope, right? 2 people pulling on a rope equally, the rope's not going to go anywhere, right? Also, they can cancel each other out. They head right at each other, equal and opposite, or equal and at each other. That's like a swinging door type of thing. 2 people on opposite sides of the door pushing, right? The door's not going to open. It's just going to kind of cancel each other out. So in certain cases, because of the geometry, these dipoles or bond dipoles end up being equal and opposite of each other, and they actually do cancel each other out rather than adding to each other. Now, if we took something like water, which looks something like this, we also know that water has polar bonds and the oxygen being more polar. So we do have polar bonds, and we could draw those bond dipoles heading towards the oxygen, which is more electronegative. So our water does have polar bonds. The geometry of our water, as we talked about, is the oxygen has 4 electron pairs, but only 2 bonds. This is our bent, our V-shaped bond angle less than 109.5, about 104-ish is about what it is. And in this particular case, we actually have kind of like a obviously bent type situation. We got the guys going this way and this way. They sort of meet at the top. You can almost think like they meet like a string at the top of it, and they kind of pull upward. You could imagine the whole molecule sort of moving. And in this particular case, they actually add to each other, and you get a net dipole moment that happens in the case of water heading in this direction, where the oxygen part of water is more negative, the hydrogen part of water is more positive, and that is the dipole moment, which means that this molecule is going to be a polar molecule. And again, if you're curious on how that sort of works, you take those bond dipole arrows and kind of put them head to tail, right? And then you connect them. You get a joining vector happening in that region. So in this case, because of the geometry, they actually do add to each other because they're not equal and opposites of each other, and they actually will kind of gain to each other, and we get this overall dipole moment. Now, clearly, nobody wants to draw vectors. Otherwise, this would be physics, right? So this is not physics. So there is really a quick way that you could kind of determine, you know, whether or not something will be polar or non-polar in terms of molecular polarity. There are certain geometries which are referred to as being symmetrical geometries. And what geometries we're talking about here are our molecular geometries. And for you guys, trying to remember what you got trigonal planar, and you have tetrahedral. And these again are the molecular geometries or the shape. And if you remember what these guys look like, when you draw the Lewis structures, there are no dots on the central atom. So basically when you draw that Lewis structure, they're all bonding electrons basically that's happening there. And if you have this situation and everything is the same element on the outside atoms, it will most likely be nonpolar molecule. So for example, if I took something like this, between carbon and fluorine, fluorine is more electronegative, which means we could draw individual bond dipoles heading towards the fluorine. These little arrows. So in this case, they end up being a tetrahedral geometry, which basically means when I look at that, I do not see dots, but everything on the outside is the same. That means that they're all going to end up in the opposite corners of this tetrahedral, which are equal and opposite of each other. So like everybody pulling from the corners of a rope, the rope's not going to go anywhere, right? And they're actually going to cancel each other out. And this guy would be nonpolar, this molecule. So again, even though it has polar molecules, because of that symmetrical geometry, all of those dipoles will cancel each other out and will be nonpolar. What would happen if I swapped out one of the fluorines, in this case, for a hydrogen? I still have my polar bonds heading towards my fluorine. What is the bond between carbon and hydrogen, polar or nonpolar? It is actually nonpolar. It has a difference of 0.4, and when you do the electronegativity, that means in this case, I have these three guys in their corners pulling, and this hydrogen is not really doing much, right? He's actually going with them a little bit towards the carbon. So you can kind of imagine those three guys are going to overpower the hydrogen, right? And kind of pull it, and you can kind of imagine that it will move. And this molecule will now become a polar molecule. So with symmetrical geometries, if you draw a Lewis structure and there's no dots on the central atom, everybody on the outside is the same element, it's going to be nonpolar. If you draw a Lewis structure and there's no dots on the central atom and everybody on the outside are different elements, or at least one different element, it's most likely going to be a polar molecule. Any questions on that? That also leaves us some geometries which are considered unsymmetrical. And if we look at those guys, which would be what you guys got left, unsymmetrical. So for you guys, you have angular, you got trigonal pyramid, and you have bent or V-shaped. And what all of these guys have in common is if you draw the Lewis structure, there are dots on the central atom, which are non-bonding electrons. And if everything is the same on the outside, in terms of the elements that are present, it will most likely be a polar molecule. So for example, if we look at water that we did a second ago, when I look at water, I see dots. I see everything on the outside is the same. This is going to result in a polar molecule. So that's really the quick way that you could probably be correct in most cases, 99% of the time, in terms of molecular polarity is dots or no dots on the central atom, and are the things on the outside the same or different. So once again, no dots on the central atom, everything the same on the outside, nonpolar, the molecule. No dots on the central atom, different elements on the outside, polar. Dots on the central atom, everybody's the same, polar. What that leaves you is really just linear, which is pretty easy to figure out. It's the straight line, right? So again, if they're going opposite in terms of their arrows, they'll cancel. If they're going towards each other, they will cancel. It is possible it's linear that they are all going in the same direction, yeah? And that would then be polar. So linear is a pretty easy one to sort of figure out. Question on molecular polarity. So, for example, if we look at some that maybe we've drawn in the past, just quickly to sketch a few here. do let's do this guy. Let's do this guy. Let's do this guy. Let's do all right, let's take a look at these really quick and see how quickly you could do polarity. And we're looking again, molecular polarity, the molecule as a whole. All right, we're going to look at this first one. The thing I should look at is the central atom, right? Do I see dots? No dots, right? And all the elements on the outside are the same, which means this guy should be nonpolar, yes? I look at the central atom on this guy. There are dots, right? Everything on the outside is the same, should be polar, right? So if we see dots and everything on the outside is the same, should be polar. This guy, I see dots on the central atom. Everything on the outside is the same. Should it be polar or nonpolar? Should be polar, yeah. This guy is diatomic. So I'm really looking at the bond, right? That bond between the nitrogens is nonpolar, which means that this is the only bond there. It should be nonpolar in this case. This guy right here, there's no dots. Everything on the outside is the same. It is nonpolar. By the way, the carbon-hydrogen bond is nonpolar to begin with, which means it's going to be nonpolar. This guy right here, polar or nonpolar? I see no dots, right? Everything on the outside, same or different? That means it then becomes polar. And it becomes polar because these three bonds are nonpolar, and that is a polar bond. So it's like that one guy just pulling, everybody else not doing much. So it's going to move and going to be polar. That would have a overall dipole moment heading in this direction. This guy would have a dipole moment heading towards the nitrogen. Bless you. This guy would have a dipole moment heading towards the heading towards the oxygen in this case, as it is more electronegative. So again, if you drew those dipole moments, that's what we could have there. Any questions on that? So that's sort of the easiest way and kind of the quickest way to do molecular polarity is really just to look at that. First off, dots or no dots, and is everything the same or different? So you'll be right again, probably 99% of the time. Weiss line going down on the sulfur? Yeah. So really on that one, it has something like this, right? Which means between sulfur and oxygen, the more electronegative element is oxygen, which means when we draw our bond dipoles, right, it's actually heading towards the oxygen, which means they're going to add and actually means that the oxygen side is more negative in this case, and the sulfur side is more positive in this case. And again, it would do kind of the same way, like, and then it would meet coming down that way. Yeah. Like it's other questions? If I drew the arrow pointing towards the top, it would imply that the sulfur would be more electronegative and electron there. Yep. Other questions? All right, that is molecular polarity. That was fun. Good times. Have I all? There we go. All right. And obviously, as we know, the geometry of CO2 is linear, so that guy is incorrect, right? So it would be a nonpolar molecule. All right, that wraps up this chapter.